Hey there, chickadees. I am writing today because we are going to be looking at logarithmic functions today. So we've discussed many different types of inverse operations and inverse functions so far. For example, we talked about the fact that addition and subtraction are inverse operations because addition undoes subtraction and subtraction undoes addition when you're solving equations. Same thing with multiplication and division and exponent or radicals, like for example, cubed root and the exponent of 3 are inverse operations, right? We also discussed inverse functions where we could write f of x and we could write f inverse of x. And when we were to look at both of those on a graph, they would be reflections across the line y equals x of each other. And the way that you find f inverse of x is by swapping inputs and outputs in f of x and solving for your output, for your new outputs, right? And so we are going to be talking today about a very specific type of inverse function or inverse operation that we haven't really discussed before. And this is going to help us to solve problems that have a variable in the exponent. So we were talking about exponential functions, and in those we have exponents in the variable. So the question is, how would I use inverse operations to say, get this x plus 4 down from the exponent so that I can find a solution? So the operation that undoes variables inside of your exponents is called the logarithm. The logarithm of a number is the exponent to which a base has to be raised in order to produce that number. So like if I have b to the power of y equals x, my base is b, y is my exponent, x is my number. If I wanted to write that as, if I wanted to apply the logarithm, then what I would be doing is I would take log base b of x, and that would be y. And so that is how I'm going to get my y down out of the exponent in my first expression. So I move it from the exponent here down into just the right side of an equal sign after I've taken the log. It's important to note that in the notation above, b is a positive number. So that means that my base cannot be a negative number and it cannot be equal to 1. So it can be a fraction between 0 and 1, or it can be a number greater than 1, but it cannot equal 1 and it cannot be negative. Also, if I write this logarithmic function, log base b of x equals y, and I change that into an exponential function, I have my outputs y in the exponent and my inputs x, right? And my inputs are my like big equals, right? So that's because log of x is the inverse function of f of x equals b to the x. So if I wanted to try to write the inverse function for log base b of x, the first thing I would do is write it with x's and y's. So I'd write it with y equals b to the power x. Then I would exchange my inputs and outputs so that I would get y equals b to the power of x. And so so that's why you see these two are inverses of each other. So they're not equal, like the exponentiation, that's what I call, hold on one second, let me erase my highlighting. So this is the exponentiation of log base b of x equals y. That means it's the equivalent version of this logarithm, but written in exponential form. This other one here is the inverse of b to the y equals x. These two are not equal. In this case, I am just saying that these graphs would be reflections of each other on the y-axis. All right, so it's important to note that b to the power y equals x is not the same as y equals b to the power of x. It's the inverse, okay? If I don't have a base written, so I just have log of x, that means my base is 10 because base 10 is our natural counting base. And actually, we can also say that if we have a base of e, then we no longer have a log, we have a natural logarithm, and we'll talk about that in just a second. The domain of log base b of x is 0 to infinity, and the range is negative infinity to positive infinity. And if you wanted to look at this on a graph, it looks like this, and it goes a little something like that. Nope, I'm sorry, that is exponential decay. It goes, how does it go? It goes like this. Like that. There we go. And this for f of x equals log of x. Then this is going to be over 1 up 0. And also, when I have an output of 1, I have an input of the base b. So this is what the graph of f of x looks like, and it has an asymptote right here at x equals 0, which is the y-axis. Right, and so we can use this relationship between the exponentiated version of the log and the log expression itself in order to solve, to write some of these expressions in exponential form. Now, this is a true sentence. Log base 6 of the square root of 6 is equal to a half. But the way to think about this is we are going to write this in a different format. We're going to write it in exponential form. And when I do that, here, let me give myself a little bit more space so I can show it. I get my b is equal to 6. My x is equal to square root of 6. And y is equal to 1/2. So I am going to write b to the power of y equals x, because that's the equivalent exponentiation. And when I do that, I get 6 to the power of 1/2 is equal to square root of 6. And this makes sense because the fractional exponent is the same as the square root, right? So an exponent of 1/2 is equal to square root. An exponent of 1/3 is equal to cube root, and so on, right? I'm going to use that same approach to write log base 3 of 9 equals 2 in exponential form. So I get my b is equal to 3, x is equal to 9, and y is equal to 2. So when I write b to the power of y equals x, that becomes, my base is 3, my exponent is 2, and 3 squared does equal 9. So that is my, that's my exponential form. I can also go from the exponential form to the logarithmic form using the same idea. I'm just going to identify b, x, and y. So in that case, I get b is equal to 2 because my base here is 2. My exponent, keep in mind I'm doing b to the power of y equals x. Right, so my exponent is y, so y is equal to 3, right? And x is equal to 8. So when I write this in log form, I'm going to write log base b of x equals y, and that becomes log base 2 of 8 equals 3. Okay, I can do the same thing with this last equation. B is equal to 10, y is equal to -4, and x is equal to 1 over 10,000. Right, so if I write this in the form log base b of x equals y, I get log base 10 of x, so I don't have to write my base because it's base 10. So log of 1 over 10,000 is equal to -4. And that means that I would do 10 to the power of -4 is equal to 1 over 10,000. So they go back and forth. We can also use this relationship to mentally evaluate logs without a calculator. So to do log base 7 of 49, I want to think, what exponent of 7 is equal to 49? And since 7 squared is 49, so log base 7 of 49 has to equal 2, because that's my exponent. And that's how I do it mentally. Even though I'm writing it down, it's like what I'm thinking in my head. For the other one, I can do what exponent of 3 is equal to 27. And in that case, 3 times 3 equals 9, 3 times 3 times 3 equals 27. So 3 to the power of 3 equals 27, which means that log base 3 of 27 is equal to 3, because that's the exponent I need on my 3 to get the 27. So I said before, a natural logarithm, and we use the letters ln for that, is a log with the base of e. So as long as x is greater than 0, we get, if y is the natural log of x, then e to the power of y is equal to x. And because those are inverse operations, the natural log of e to the x is just x. They undo each other. And e raised to the natural log of x equals x. So I can raise both sides of an equation to the power, like if I can do e to the both sides to get rid of a natural log of x if I'm solving, or I could take the natural log of both sides to get rid of an exponent if I have a base of e. All right, so they're inverse operations and they can be used in solving equations. We're going to do that more next class, but I just wanted to make sure to talk about it so you understand how this ties in to our whole exponential version versus our logarithmic version. Okay. Now, if you want to use a calculator to evaluate logarithms, which is definitely the easiest, you have to use a change of base because calculators only use base 10 or base e. So you either can use the natural log or you can use log base 10, but you can't find log base 3 of 6, for example, in a calculator without changing base. So our change of base form is our log with a base b of x. No matter what b is, I can rewrite that in a different base, say base d, as log base d of x divided by log base d of b. So I'm going to show you how to do that using log base 3 of x. I'm going to show it using a base of e and a base of 10. So I can do log base 3 of 6 is equal to log base 10 of 6 over log base 10 of 3, right? And if I put that into my calculator, then I get here, I think I can just type this in here. Let me see, let me give it a try. I think I can do log base 3 of 6 equals, no, hold on, let's try it like this. Log of 6 divided by log of 3 equals, there we are. Yeah, 1.63092. Oh, a whole bunch of stuff. But that's the idea. Hold on, let me make this a little bit bigger. All right, and then also, this isn't going to change anything, but I just wanted to do it. I can also use the natural log. I could say log base 3 of 6 equals natural log of 6 over natural log of 3. And if I do that, I can type that too. Let's do this. I'm going to make my stuff bigger. I'm going to say natural log of 3 divided by natural log of 6 equals, and there we go. Look, it's the exact same thing. Oops. Oh, I swapped those. Natural log of 6 over natural log of 3 equals, there we go. And you can see they're the same thing. And the reason I knew I had done something wrong was because I didn't get the same thing when I wrote it. So that's how I knew I had swapped which was in the numerator and which was in the denominator. All right, so you can see that they're equivalent. It doesn't matter which base you change to, so long as you do the log of the x over the log of the base in your new base, okay? This is the same whether you use a graphing calculator or your calculator on your phone. You just are only going to be able to calculate logs with base 10 or natural logs. Right, so now we're going to talk a little bit more about the graph of the function f of x equals log base b of x. I am going to graph this on Desmos real fast. Actually, I'm not really going to worry about that yet because I do have a nice little graph we're going to use when we start talking down below. So here's what I'm going to do. I'm going to draw my little graph. All right. And we know that log base b of x has an asymptote at x equals 0, meaning that it's never going to touch the x-axis. Also, keep in mind that this is the inverse of my exponential. This is the inverse of an exponential function. And that means that when my exponential function is growing, like, you know what? I'm not going to worry about it right now. I feel like I know that that's confusing, but I just want to make sure that I'm doing the exact right thing here. All right. So f of x equals log base b of x is my parent function. It has an asymptote at x equals 0. As you can see, the domain is all numbers greater, like where my x is positive. My domain is only positive numbers, so x is from 0 to positive infinity. My range goes from negative infinity to positive infinity because I can go from here up or from here down, and I still wind up with values. So my domain is 0 to infinity, and my range is all real numbers, or from negative infinity to positive infinity. The graph of log b of x crosses the x-axis at the point over 1 up 0. All right, and my input that gives me an output of 1 is my base of b. And we are going to call that like a key point or a critical point. There's no y-intercept for the graph of f of x equals log base b of x because it can never equal 0. It has that asymptote. And this graph will be increasing if the base is greater than 1. So, and it'll be decreasing if our base is a proper fraction. So if it's between 0 and 1. And that makes sense too with our inverse of the exponential function, because our exponential function increases when your base is a whole number and decreases when your base is a fraction. That's our exponential decay. But the log is the opposite, right? Because we're swapping it. And so here I have an increasing function as long as b is positive, and I have a decreasing function if b is a fraction. But b can never be negative, so that's important to know. B will never be negative because that would give me what's called a harmonic function, and you don't deal with those until your second semester of calculus, maybe even your fourth semester. All right. So one thing is if you are told to graph the function like log base 2 of x, sometimes it's easier to think about making a table of values for the exponential version of that, and then swap the x's and y's to get the inverse, right? So for me, if I have a base of 2 and I have my exponent of x, keep in mind this is the inverse function, so it's not log base 2 of x equals y. I have y equals 2 to the x, like it's the actual inverse option. That means that x is my exponent. Then what I'm going to do is I'm going to make a little table of values for x and for 2 to the power x. I'm going to let x go from 0 to 3. All right, and I'm just going to find my values of y if those are my exponents. So 2 to the power of 0 is 1, because any number raised to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. And I'm just doubling each time. Now I'm going to swap those, and that will give me my input and output for log base 2 of x. All right, so now my outputs are going to go from 0 to 3. And my inputs are going to be the outputs when I used my exponential form. So my inputs are going to be, whoopsie, 1, 2, 4, and 8. So that means that on my graph, I would graph the points 1, 0, 2, 1, 4, 2, and 8, 3 if I wanted to graph f of x equals log base 2 of x. Right, so you don't have to use that method, but if you're graphing by hand, that can be a little, whoopsie, that can be a little bit easier than graphing. You know, it can be easier to think about the swapped inputs and outputs when you are trying to come up with your ordered pairs. You can always just graph on decimals though. All right, so now the other thing I'm going to talk about before the end of our little lecture here is the fact that I can transform my graph f of x equals log base b of x, just like I could any other function. It's a one-to-one function, so I have no troubles like doing any of the transformations on it. So for example, if I wanted to do a horizontal shift, right, then I take my normal graph that I would have for f of x, and I'm going to shift it by a factor of h. If h is positive, then I shift to the right, and if h is negative, I shift to the left. So I'm going to do a little example like that. So keep in mind that in this case, the asymptote shifts along with my x-axis. So if I have a positive value of h, that would be a positive shift to the right. I might see x minus h in my equation, but x equals h becomes my asymptote. And then I repeat this graph exactly as I see it, but it's just going to be shifted to the right. I don't think I drew that exactly perfectly, but I hope that it's good enough to where you can see what I'm trying to get at. My the point, the asymptote shifts to x plus 8 or to h. All right, my x-intercept goes from 0, 1 to h1, and that's because like if you look over here, I do 0 plus h, like I add my shift into my x factor, and so that means that this is just going to be the point h comma 1, and my new point here, instead of b comma 1, I get 1 plus h comma b. No, wait, that's not right. What I just said was wrong. Actually, this is wrong too. So that would have been right for 1 comma b, but I want to find b comma 1. In that case, I would get b plus h comma 1. All right, and so the same thing's going to happen over here. This is b plus h comma 1. Sorry for the little error. All right. If h was a negative number, then this is f of x minus h if h is greater than 0. If h is less than 0, then I would shift over here however many units h is. Right, so this is when h is greater than 0. When h is less than 0, I still get the exact same graph. All right, except that my intercept is still going to be at h comma 1, and my value of my base is going to be b plus h comma 1. And so it'll just shift to the left or right, just like we've done with all of our horizontal shifts. If I want to shift it vertically, okay, so if I want to shift my graph vertically, I am going to add in my vertical shift factor. The parameter is k. All right, so if k is greater than 0, my graph shifts up, and it shifts down if k is less than 0. The vertical asymptote is unchanged. I still keep it at x equals 0. All right, the domain and range are unchanged, whereas above our range is still negative infinity to positive infinity, but our domain starts at whatever h is, because that's where our vertical asymptote is, instead of starting at 0. Here, though, in a vertical shift, I just am sliding it up or down, so I keep my same horizontal or my vertical asymptote, and my domain and range are unchanged. So the first thing I'm going to do is sketch the asymptote, and I'm going to find how the shift, so I'll draw my x equals 0, and I want to see how the shift affects the points 0, 1, and b1 from the parent function. So my asymptote remains unchanged. My point 1, 0 is going to go to 1, and then 0 plus k. So it'll just become 1 comma k. And my point b1 becomes b, and then my 1 shifts by k units as well. So I'll add k to that. Of course, if k is negative, that's going to decrease that point. If k is positive, it'll increase it. So a shift up from this would just be this exact same graph shape, but just a little higher up. And in this case, my point over 1 up 0 would become 1 comma k. And my point B1 would shift by k units up. And I would get B comma 1 plus k. And if I wanted to do a negative, like if k was less than 0, I still get this same graph. But instead of having k be greater than 0, we're going to make k less than 0. In that case, I would still get the same coordinates, but they would just be a negative number instead of a positive number. So I'd get still 1 comma k, and I would get b comma 1 plus k. But in this case, k is negative, so that number would actually be less than 1, right? And I'm just shifting down by k units for each of them, okay? For a vertical stretch or a compression, I just multiply a stretch factor, a, times f of x, which in this case is a times log base b of x, right? So there's a lot of changes that are possible based on whether a is greater than 1, well, whether the magnitude is greater than 1, whether the magnitude is between 0 and 1, or whether we have a negative number. So we still have our vertical asymptote at x equals 0, and our domain and range are unchanged. But the way that we do this is our asymptote stays the same, but the point 1 comma 0, my y factors, all my points x, y are going to change by y times a. So I do my x's stay unchanged. So x goes from x equals 1, y equals 0 goes to x equals 1, y equals 0 times a, or 0. So I'm still going to intersect the same x-intercept. And then my point b comma 1 is going to become b comma 1 times a, which is just a. So if a is a number that's like greater than 1 whole, then that's going to shift this up. Think of like a steeper slope. So it'll still cross there at 1, but it'll be much steeper. And this point is going to become b comma a. Right, so I still have 0 comma 1. This is if absolute value of a is greater than 1, right? If I want to look at what happens when a is a fraction, I'm still going to have the same x-intercept, but it's going to be a more gradual increase. So it'll be smaller than it was before. And this is if 0 is less than a is less than 1, all right? In the event that a is negative, it will still stretch or shrink in the same way. Like a negative number greater than 1 is going to make it steeper. A negative number less than 1 is going to make it more gradual. But just making a negative 1 is just going to flip it completely upside down. So in that case, I would get, it would look like this. Nope, sorry, it's kind of hard to do. It'll look like that. Alrighty. For a horizontal reflection, that means that I have a negative inside of the parentheses. The number inside of the parentheses is called the argument. So the argument of my function is negative. If that happens, I'm flipping over the y-axis. So my graph will remain unchanged in any way, except that I'm going to be, whoops. Oh my goodness, I don't want to make you seasick, but I do need to find where I was. Okay, there we go. That would mean my graph is going to look, oh no. Let's see, I don't think I'm screen sharing anymore. Hold on, I will screen share now.